Okay, so for number 5, we have a 475 centimeters cubed, so that's volume, sample of gas at 0 degrees Celsius, so we never want degrees Celsius. From the front side, we have this equation, kelvins is equal to degrees Celsius plus 273. So I'm going to add 273 to 0, which is just 273. Oops, no degrees. Kelvins. And we have 1 atmospheres, which is a pressure, is allowed to expand until it occupies a volume of 600 centimeters cubed. At what temperature would be needed to return the gas to 1 atmosphere, which is a pressure, at its new volume? Okay, so we can see that we have 475 for our initial volume, so 475, and our initial temperature is 273, and our initial pressure is 1. So it's allowed to expand to 600 centimeters cubed, so that's our new volume. What's the temperature? So question mark there. Would needed to return to 1 atmosphere? And we're not given any n value, so we can cross that out and assume it's constant. Do we see how the pressure is also the same? So I'm just going to cross that out as well. Okay, so I have temperature and volume. So temperature and volume. I have this big equation, but I'm only writing the variables that are not constant. So I'm only going to write volume and temperature when I copy the equation over. So V1 over T1 is equal to V2 over T2. And then I cross multiply. So V1 T2 is equal to T1 V2. Now I plug in. So my initial volume is 475. My final temperature is, I don't know, so I'm going to just put T2. My initial temp is 273. My final volume is 600. And from there, I can solve things out. So I've run out of space. I'm just going to kind of put it up over here. So on the left side of my equation, I just have 475 times T2. And then on the right side of my equation, I can simplify this. So 273 times 600. And I have 800. I want to isolate T2, so I'm going to divide each side by 475. Cross out 475. Divide by 475. And I end up getting T2 is equal to 344.84. And that temperature is in kelvins.